Okay, let us start. So first, the results of the controller work are rather good. So actually, I do not plan to discuss solutions of problems if you do not have questions. Maybe I would just say a couple of words about problem 2b. So I recall that here you have some Markov chain, and in the first question you should find mean time when you arrive to some specified state of this Markov chain. But in the second question we ask what happens if the process continues during a long time. And here I don't know why, but not so many people found a solution to this problem. But here you just need to find the stationary state of this Markov chain, because the matrix of this Markov chain is mixing, so the Markov chain is ergodic, and it means that when the process continues during a long time, you can predict probabilities of being in a given state. This is just stationary probability of this state, right? So you just need to find the stationary state of this Markov chain and to refer to the ergodic theorem. Okay. So now let us pass to the lecture. So today I plan to discuss some another applications of Markov chains, but these will be applications in mathematics. This will be some link between the Markov chains and the linear algebra. So how you can make some nice conclusions in linear algebra using the Markov chains. So this will be the Perron-Frobenius theorem. This is quite famous theorem, Perron-Frobenius. Theorem. This is first proven by Perron in 1907. Of course, he proved this by means of linear algebra. He didn't use Markov chains because they was just created at around this year by Markov. So this theorem, of course, it can be proven by purely linear algebraic methods, but we will discuss some simpler proof which is available because of the Markov chains. So for this theorem, I will slightly change my notation. I will denote the row vectors. So before when for row vectors I wrote V, and for column vectors I wrote V transposed, right? But for this theorem, since we are talking about the linear algebra, I will change the notation for standard notation in linear algebra. By V, I will denote column vectors. And for row vectors, I will write V transposed. Okay, so this is only for this theorem. Now, statement of the theorem. So this is, as far as I checked, this is theorem number 33, Perron-Frobenius theorem. States the following. So let A, B, L times L matrix. L is more than or equal to 1, which is with positive elements, strictly positive elements. Oh. With strictly positive elements. I recall that we denote these matrices with strictly positive elements like that. A is more than 0. So this is the only assumption I make. Then, first, there is a positive eigenvalue of this matrix of A, and corresponding to it positive left and right eigenvectors. Left and right eigenvectors. Eigenvectors, I want to denote the left one by F and the right one by E. So it means that components of these eigenvectors, Fj and Ej, are all positive for any j. I recall that we also write in this case E and F more than 0. So this is notations which I accept in this course. So that is F. So it should be row vector, right? So F transposed A equals to lambda A, or to lambda F transposed, and A E equals to lambda E. So what is the assertion? The assertion is that it is not even evident that the matrix A has a real eigenvalue, right? So because all its eigenvalues can be complex, but it turns out that in the case when its elements are strictly positive, it has at least one real eigenvalue, and moreover, this eigenvalue is positive, strictly positive. And moreover, the eigenvectors which correspond to this eigenvalue are also strictly positive. So this is the assertion. So the second assertion of the theorem is that these left and right positive eigenvectors of the matrix A are associated to the eigenvalue lambda are unique. So, for example, for the right eigenvector E, it means that if you have another V equals to lambda V, and V is positive, it means that V is proportional to the right eigenvector E, where E is from item 1 of the theorem. and similarly for the right eigenvector f. And the third assertion, which is the most interesting one, it says the following. It says that if you take your matrix A to the power k, and then if you and what are you interested in? You are interested in the behavior of this object when k goes to infinity. Just for arbitrary metrics, it can be a very complicated object, right? You take larger powers of the matrix, and in general you can say anything. But it turns out that in this specific case, when the matrix A is strictly positive, it behaves exactly as lambda to the power k. More precisely, where lambda is this strictly positive eigenvalue. More precisely, the theorem states the following thing, that A to the power k divided over lambda to the power k converges when k goes to infinity to the following matrix. I should take vector, which one is the first? Vector E, and then I should multiply it by the vector f. So look, since the vector E, this is a column vector, and the vector, f transposed, and the vector f transpose, this is a row vector, right? Then when multiplying them, I obtain L times L matrix. So a matrix of the same size as the matrix A. Okay, so this is the assertion of the theorem. Where you can have questions like that, for example, when you have some linear dynamics and you are interested in the limiting behavior, and then exactly you need to study the behavior of this matrix A to the power k if this matrix gives your linear dynamics. Okay. Do you have any questions concerning the assertion of the theorem? If no, I'll start proving, but no, before the proof, I'll give an example. So as an example, let me consider the case when the matrix A is stochastic. Let A be stochastic. And as in the theorem, positive, strictly positive. Then, in fact, in this case, there is almost nothing to prove. Just let us look what is going on in this case. So, what the question for you? What is in this case the vector E? What is the vector E? I recall the stochastic. It means that sum of its components over the row equals to 1, right? What is the vector E? Steady state? No, the vector F is a steady state. So F is a steady state. So F transposed is a steady state. Because F transposed A, this equals to lambda F transposed, right? So, but now for the moment we do not understand what is lambda. So, okay, let me take for E the vector, the column vector, which consists of only of units, right? Then what do we have? Then we have that A times E. This is just sum of what makes multiplication by this vector. It takes a sum over row of the matrix A. So it means that we obtain again this vector E. It means that lambda, this is our lambda, it equals to 1. It equals to 1. And yeah, in fact, this lambda is determined uniquely. This is some another item of the theorem, which I think I will leave as an exercise for your homework. So if you found one lambda which is strictly positive and which corresponds to positive eigenvectors, then this is unique. Okay, and then for this lambda, what do you have? If you take steady state, then you have this relation. So it means that indeed we can just immediately find this E and this vector F, right? And then the ergodic theorem implies, since the matrix A is strictly positive, it can be viewed as mixing transition probability matrix for some Markov chain because it's stochastic, right? So this can be seen as transition probability matrix. And then ergodic theorem implies that when you take this matrix to the power k, then it converges, moreover, it converges exponentially when k goes to 0 to which matrix? To the matrix which has in rows the components of the vector f, f1 fl, f1 fl, etc., f1 fl. But this is exactly what we claim in the theorem, because the matrix E, this is just the vector E, this is just this simple vector, right? So this is indeed EF transposed. So in this special case, when the matrix A is stochastic, the theorem immediately follows from the ergodic theorem. Here I discussed only item 1 and item 3. I didn't discuss item 2, but I'll prove it for the general case. Okay, is it clear?
Yes.
Proof of the theorem. So now let us turn to the general situation. First, we need to show that indeed there exists positive eigenvalue associated with positive eigenvectors. So to this end, let us consider the space of all distributions. So, well, this isn't a space, right? Because it's simplex set of all distributions. So these are non-negative vectors such that the sum of their components is 1, right? So this is our usual notation. And let us consider the following mapping defined on this set. I will denote it A hat. So it acts on row from row to itself, and let us define it as follows. If I take vector H, then the action of this mapping A hat to H, its component number I, is given by sum of A, matrix A, it should have components A, I, J, right? Sum of A, I, J times H, J divided over yeah, so since I need this guy to act from row to row, I need that the sum of all components over I should be equal to 1. That's why I need to normalize this object. I need to divide over sum of this guy over I. Up. Sum over J, A, I, J, H, J. Perfect. So this is indeed the mapping from row to row, right? Since the sum of all components equals to 1, and clearly everything is non-negative here. Clearly A hat, this is continuous mapping. It is not linear. Look, this is not linear because you have this denominator, but this is continuous. Continuous. So this is a continuous mapping of a compact set to itself. Then by Brouwer fixed point theorem, there is such a vector H from rho that A maps this vector to itself. Perfect. But what does it mean? What does it mean? Look, it means that sum over J, A, I, J, H, J. So now I'll write this component wise for the component number I, and I will multiply left and right hand side of this equality by this denominator. This equals to the sum over I, sum over J, A, I, J, H, J times HI. Very good. Let us denote this object by lambda. And what is written here? Here it is written exactly that A times H equals to lambda H, right? Lambda is clearly strictly positive because all components A, I, J are strictly positive, right? And the sum of components of H, J is 1. And also clearly this vector. So it remains to show that that all components of the vector H are strictly positive. That Hj is positive for any J. But this is clear because it follows from this equality. What is Hj? Hj equals to lambda to the power -1 multiplied by the component number J of this guy, but this is exactly sum over I, A, I, J, H, J, but this is strictly positive since all A, I, J, they are strictly positive, right? And if this is 0, then it means that all components of H, J are 0, but this is impossible since H belongs to the space of distributions, and the sum of its components should be equal to 1.
I think that the last sum is by J, not by I.
The last sum is,
yes, the sum that we used to show the positivity.
Just wait. No, no, it is.
Oh, no, yes.
Yes, thank you. This is, yeah, so this should be like that here, HI, and here, yeah, thank you, you're right. Here, this is AJI, right? Because I need the component. Thank you. Yeah, so look, we have found the right eigenvector. So E equals to this H, right? E equals to this H. Nice. But then, similarly, we find some possibly another eigenvalue mu and vector F such that F transposed A equals to mu F transposed. So look, I do the same thing, but instead of multiplying from the right by H, I multiply from H transposed from the left, and by the same argument, I find the left eigenvector with positive components, as well as the eigenvalue, which is strictly positive. But possibly this eigenvalue will be different from lambda. It isn't clear why it should be the same eigenvalue, right? So now to conclude the proof of the first item of the theorem, which affirms that left and right positive eigenvectors are associated with the same eigenvalue. To conclude the proof of this theorem, it remains to show that this lambda we have found coincides with this mu, right? So it remains to show that lambda equals to mu. Nice. How will we do this? Let us just take the scalar product of vectors f and e. This scalar product can be written as f transposed times e, right? Just scalar product of vectors f and e, standard scalar product in Rn. And let us multiply this by mu, okay? Then what is written down here? The following thing, ft times a times e, right? Because this guy, it gives exactly mu times ft. But this guy gives ft times lambda times e, because this guy, it gives lambda times e, right? Well, it means that either lambda equals to mu, or this factor f transpose times e equals to 0. But this is impossible. This possibility doesn't exist. Why? Why? How do you think? Just remember that everything we are doing is very simple. Why is it impossible? Since all components,
they are positive, yes.
Yeah, exactly. All components of these vectors, they are strictly positive. But what is written down here? This is just the sum of fj times ej over all j. So this is strictly positive. Okay, so we have proven the first item of the theorem. Let us pass to the second item of the theorem. What did we affirm here? We affirmed that left and right positive eigenvectors associated to the eigenvalue lambda. Sorry. I apologize. I formulated this item not correctly, because this phrase associated to the eigenvalue lambda, it is not correct. I mean, I should eliminate this, because the claim is strong. Just left and right positive eigenvectors are unique. It means the following: if you found positive eigenvector with some eigenvalue mu, it means that this eigenvector will be proportional to the eigenvector e, and accordingly mu will be coincide with lambda. You see, so this is stronger. Yeah. So how will we argue in this case? In this case, okay, yes. In my notes, it is written that this is a homework. So this is a homework. Perfect. Homework. Well, then let us pass to the proof of the most interesting third third item. Third item affirms these conversions. So in the example, you have already seen that at least in this special case, the convergence is implied by the ergodic theorem. So let us then also use in the general case the ergodic theorem, but the problem is that the matrix A is not a stochastic matrix. So let us try to construct the stochastic matrix. Yeah, so let me also note that my formulation of the third item is not correct. Of course, why? Because the eigenvectors are defined up to multiplication by a constant. So if I multiply these eigenvectors by a constant, I mean, it is nonsense because the limit should be unique. So I should say something here about the normalization of this eigenvectors, and the normalization is as follows, where E and F are normalized in such a way that their scalar product, so F transposed E, equals to 1. Okay, equals to 1. In fact, this normalization is sufficient because you see this object depends normally for two eigenvectors. You need two normalizations, but here only this normalization is sufficient because this object depends only on product of components of E and F. Okay. So now let us, to prove the third item, let us construct the following matrix. Let us take the matrix pi with components p, I, j, given by the following. I think we should take lambda e I, or just no, sorry, I am mistaken. This should be a I j e j divided over lambda e I divided over lambda. Sorry, here ej. Here ej. This is some computation which shows that this matrix is okay. So I do not remember the formula. This is ej, and in the denominator it should be ei. Yeah, like that. Like that. So my plan is to show that P is stochastic. Then, so this will be A. Then B is to find its stationary state, and I claim that its stationary state has the following form: E1 F1, E2 F2, etc. EL FL. This is stationary state of this matrix pi, and clearly this matrix is, if it is, we have shown that this is stochastic, then it's clearly that this is mixing, because it's strictly positive, and then C we will use the ergodic theorem to study P to the power k, and then we will associate this with A to the power k. Okay. So this is a plan. Let us realize it. So item A. We need to show that this matrix is stochastic. To this end, we need to sum up all if its components over rows. So this is, look what it gives. It gives, when I sum up over J, it gives matrix A times the vector E, its component number I, divided over lambda EI, but this is exactly lambda EI divided over lambda EI, since E is the right eigenvector. So this is exactly 1, right? So this point A is okay. So let us look at the point B. Then we need to check that P times large P equals to P. So let us make the computation. Look, what do we have? We have, let us compute the component number J. We have summation over I, EI FI multiplied by P IJ, so this is AIJ EJ over lambda EI, so EI are cancelled. Then look, here we have action of the matrix A to the vector F transposed from the left. So this gives lambda times F Fj EJ, and this should be divided by lambda, and we get exactly Fj EJ. So this is what we need, because it's component number J of the matrix of the vector P pi. And then it remains to check. It remains to study the power of the matrix A, and let us do this. Look, what is the relation between the matrix A and the matrix pi? Aij equal to lambda EI times Pij over EJ, right? Over EJ. Then oh, if I wish to find the component number, say Km of this matrix, then what should I write? Then I should write down the following. I should write down, first I will have lambda to the power k, and you see lambda to the power k already appeared. Then you have ek over summation over I1, I2, etc. Ik minus 1 ek pk I1 over EI1. This is summation over. So let me write it. Let me write it better. Summation over I1, I2, etc. I k minus 1 over I1. Then what we have? We have EI1, PI1, I2 over EI2, etc. And the last one will be EIK minus 1, PIK minus 1. Wow. Sorry, I have some problem because I have two different k's, so let it be n instead of k. And then here I also should replace k by n. Yeah. IK minus 1m over EM, right? Then look, this E are cancelled, and so on. This will be cancelled everywhere, and in the result, you will get lambda to the power k times En over Em, and here you'll have the matrix P to the power k. Its component number nm, right? But then by ergodic theorem, we know that this guy converges even exponentially to the component number m of the stationary state of this matrix. But the stationary state of this matrix, we have already computed it. Sorry, I cannot write down convergence because I have here lambda to the power k. So that's why first I need to divide the both sides of the equation over lambda to the power k. And then for this guy, I can already say that it converges somewhere, namely it converges to En over Em, and then component number m of the steady state, and this is Em times Fm. Look, Em is cancelled, equals to En times Fm. But this is exactly what we wanted to prove, since we wanted to prove that a to the power k over lambda to the power k converges when k goes to infinity to the product E times F transposed. Yeah. Okay, is it clear?
Yes.
Clear? So of course, as I told you in the beginning, this theorem can be proven without employing the Markov chains. But we see the proof with Markov chains, it's nice and simple. The proof with methods of linear algebra will be much more complicated. So, and this works in the both sides, because of course the ergodic theorem, it can be proven by means of linear algebra purely without using stochastic techniques we have used. But sometimes it's simpler to use stochastic techniques. Sometimes it's simpler to use linear algebraic techniques. So for this theorem, I think that this is the simplest way of proving. Okay, so which time is it? Now we have another 30 minutes. Perfect. Because then I will change the subject. So in principle, one possible plan for the end of this lecture is to discuss some another linear algebraic algebraic aspects, just to explain how the ergodic theorem works from the point of view of linear algebra, and to prove some maybe simplified version of the ergodic theorem purely by linear algebraic techniques. But I think that it's more interesting to discuss another subject which I'll start today and I'll finish it the next time, because I think that the control work, it will be the next time the control work, it will be shorter than for whole lecture. So part of the lecture I will spend to continue the subject which I will start now, and the subject I will call it topology of Markov chains. Not topology, maybe topological structure of Markov chains. So what is my motivation? My motivation is the following. First, I understand that we are doing something rather simple, right? We are studying only finite Markov chains. That is, Markov chains with finite number of states. I mean, well, not all the theorems I've proven they affirm something about finite state space Markov chains, but the principal theorems like the ergodic theorem, I've proven it only for finite number of states Markov chains. But even in this simple case, we do not have for the moment a criterion which would say the Markov chain is ergodic if and only if something happens. We have some sufficient condition, which is good. The sufficient condition says that the Markov chain is ergodic if its transition probability matrix is mixing. This is a good sufficient condition. We have seen a number of applications where this condition is fulfilled, but still we would like to have some criterion when the Markov chain is ergodic. We understand that this sufficient condition, which is the mixing property of the transition probability matrix, this is not necessary condition. This is not necessary because we have a very simple example. And there was a problem devoted to this example. This was a last problem before the control work. I think this was like set 5, problem number 5. I don't remember exactly. If you consider a Markov chain with such graph, clearly its transition probability matrix is not mixing. Because if you arrive to the state 1, then you stay here forever. But the Markov chain is ergodic, and even it's exponentially ergodic. And morally, intuitively, it's quite clear because I mean, the probability that you do not pass over this arrow, that you never pass over this arrow, then you always are here. This is exponentially small, of course, and then once you pass to this arrow, you stays here, right? I repeat that there was a problem devoted to this situation. So, and in order to provide a criterion when the Markov chain is ergodic, we need to discuss what can be else like, and so now I would like to show you structure of all possible Markov chains with finite number of states. To this end, I will need to introduce some notation. So what do we have? As usual, we have X. This is a state space. We assume that the number of states is finite. So you can think that the state space is just 1 from 1 to L, if you wish. Then we have some transition probability matrix pi with components p, a, j. So this matrix is, so the associated to it Markov chain is homogeneous because the transition probability matrix does not depend on time. And then I will write I arrow j, and I will say I leads to j, leads up. If there exists k which is strictly positive, wait, no, which is not strictly positive, zero, it's okay, such that in time k, in k steps, the transition probability from I to j is strictly positive. I recall this denotes the transition probability in k steps. So here you have your state I, here you have your state j, and you you can find a path, say in k steps, which goes from the state I to the state j. Okay. So this is the first definition. Then I will denote like that, errors in both sides, and I will say I communicates with j if I leads to j and j leads to I. Okay, so if you can go from I to j in some k steps, and then in some possibly another number of steps, say m steps, you can go from j to I. Since this k is more than or equal to 0, it's clear that I communicates with itself, right? It's clear. Then for any state I, then it is clear that if I communicates with j and j communicates with k, then I communicates with k. And also by definition, if I communicates with j, then this is equivalent that j communicates with I. So what does it mean? What does it mean?
Communication is an equivalence relation.
Yes, exactly. This communication gives an equivalence, is an equivalence relation. This is an equivalence relation. Then it means that the set of all states x can be decomposed to a finite number of equivalence classes. This is equivalence class, and we will call it communicating class. Communicating class. Let us give an example. So let us consider the Markov chain with the following graph. You have Okay, you have such a triangle. Then from 2, for example, you can go for 2. Then you have the state 4. You can go like that. Then you have states 5 and 6, which communicates up, and then you have state 7, from which you go only to itself. Up like that. Well, and what are the communicating classes in this example? Look, this is the first communicating class, right? I'll call it x1. This is the second communicating class because 4 communicates only with itself, x2. This is the third communicating class, x3, and this is the last communicating class, x4. For communicating class, I will say that a class xi leads to class xj if, so this is definition, it's another definition. If, well, I'll write it informally. It is possible to go from the class xi to the class xj. Look, in our example, the class x1 leads to the class x2. The class x1 leads to the class x3, and then the class x2 leads to the class x4, right? To the class x4. No, this isn't all because also since x1 leads to x2 and x2 leads to x4, then x1 also leads to x4, right? x4. This relation leads to gives a partial order. Partial order on the set of communicating classes. Since it gives partial order, there exists minimal communicating classes. Minimal communicating classes, which are defined as minimal elements according to this order. Minimal elements according to this ordering. And I will denote their set E be the set. Well, this is also the definition. E be the set of minimal. This is not definition but notation. Minimal communicating classes. In our example, who are minimal communicating classes? Who are minimal communicating classes? Guys, who are minimal classes? No, minimal in the other direction. In the other direction. So I say that up like that.
Okay. Okay. Then it is x4 and x3.
x3 and x4. right? These are minimal guys, x3 and x4. So actually, who are these sets? These sets are the sets where you arrive and then you live there. Since once you arrive to the set x3, then you live there forever. The same is true with the set x4, which actually consists of the unique state. Another definition. This is a standard definition, often used. States J belonging to wait. Sorry, no. My previous definition was bad, because E is not a set of minimal communicating classes. This is a union of minimal communicating classes. A union of minimal communicating classes. What is the difference? The difference is that E is then union of the sets x3 and x4. So it consists not on the communicating classes, but it consists of states, right? So yeah, so in our example, it equals to state 5, state 6, and state 7. 5, 6, 7. States J, which belongs to the minimal communicating classes, to E, are called essential. Called essential. And states J, which do not belong to the set of to these minimal communicating classes, are called inessential. Inessential. In Russian, this is несущественное состояние. Несущественное состояние. And this is существенное. Существенное. Okay. Just a second. Let me plug my computer. Otherwise it will stop working. Okay, let's continue. So these states are called inessential. And lemma. I will not prove this lemma because not because this is complicated, but just to economize time without the proof. So this is lemma number 34, as far as I understand. The first, so it's better to write the other way, lemma 34 without proof. It affirms first that the probability that there exists such n large that your Markov chain psi n belongs to the essential set. Psi 0, psi 1, psi 2, etc. This is your Markov chain with arbitrary initial condition and the transition probability matrix phi, right, as usual. And there exists n such that probability that psi n belongs to E for any to the set of essential states for any n larger than n equals to 1. Item B affirms that the probability there exists lambda from 0 to 1, strictly less than 1, and a constant c which is positive, such that the probability that psi n does not belong to the set of essential states is less or equal than, as usual, constant times lambda to the power n. Look, this is in fact exactly your exercise, which I already mentioned from your homework. Look, it affirms that if you take this Markov chain, then the only essential state, this one, right? Essential. It's an essential state, and it affirms that if that with probability 1, there exists a moment of time when you arrive to this state. This is the first item of lemma. The second item affirms that the probability that you are not yet arrived here decays exponentially. For this,
sorry, but then we need another sign, like psi n does not belong to E.
Wow, thank you. Yes, you're right. You are completely right. Yeah, you're right. Does not belong to you. Oh, does not belong to you. Yes, and for our second example, for this one, it means that the probability that you are not yet here and you are not yet here, it decays exponentially, right? And that for almost every omega, you will arrive either here or here, right? This is the first item. So that's why these states are called essential, because if you wish to understand what is going on when time goes to infinity, only these states matter, right? Only these minimal equivalence classes matter, because earlier or later you will leave this part of your Markov chain. In fact, then there are two possibilities which object can be studied. You may ask first question, well, what is going on after you have arrived to these essential states, right? If you have something like mixing or not, like ergodicity or not. The second type of questions which can be asked is how exactly you leave these states and you go either here or here. If it is possible to find probabilities with which you will arrive here and with which you will arrive here. So these are two different types of questions, and I will concern only the first type of questions. So what is going on here? Accordingly, I introduce the following definition. A Markov chain is called irreducible in Russian. This is неприводимое. if it has a unique minimal equivalence class. No, sorry. Not minimal equivalence class, just a unique equivalence class. Sorry, communicating class. Communicating class. Look, for example, such a Markov chain, it is irreducible because it has clearly a unique communicating class. This Markov chain is not irreducible because it has 4 communicating classes. And if this Markov chain, which is drawn here, is irreducible or not? Clearly not, because it has 2 communicating classes. The first one is this one, and the second one is this one. So now I'm interested in irreducible Markov chains because of the following. Because my lemma 2034, it states that earlier or later I will arrive to a minimal communicating class, right? Either here or here. And from now on, you can forget about the rest. If you arrived here, you can forget about the rest of the chain, and like that, you are living in only in one communicating class. Then you can consider Markov chain without this part. That is irreducible Markov chain. Okay. So somehow we reduced our problem to studying irreducible Markov chains. Irreducible. What do I want to say next? Okay. Yes. So this is the last thing I will do for today. I think I will define a period of states. So now let us consider an irreducible Markov chain. Reducible Markov chain. So definition. Period of a state I. This is a number which I will denote d of I, which equals to greater common divisor of k, which are more than or equal not to 0 now, but to 1, such that the probability to go from I to I in k steps is strictly positive. For example, if you have Markov chain which consists of 2 states, such simple Markov chain, then period of state 1 equals to the period of the state 2, because it's clearly symmetric, equals to 2. Look, because you can arrive starting from the state 1, you can arrive to the state 1 in 1 step. You cannot, but in 2 you arrive to the state 1. Then in 4 steps, of course, you can also arrive to the step 1 and so on. So more precisely, in 2n steps, you arrive from state 1 to state 1. That's why the greater common divisor is 2. Of course, for such a chain, the similarly also periods of all states are the same and they're equal to 3. If I modify this chain by adding possibility to go from state 1 to the state 1, then the period will become how much? What is the period of this chain? 1. Yeah, 1. Because look, let us check it. So let us check it for one state, for example, for the state 2, the probability to go from state 2 to state 2, you can go in 1, 2, 3 steps, right? In 3 steps, but you also can go in 1, 2, 3, 1, 2, 3, 4, in 4 steps as well, right? So these probabilities are positive. That's why the period of the state 2, the period of the state 2 is 1. Well, let me give the last example, because I think that this example, yeah, I will need this example later. Slightly more complicated. Let us consider the chain of the following form: 1, 2, 3, 4, 4, 5. Yeah, like that. Then here you go over the square, and also you can go to the state 5 and to return from the state 5. Like that. What is the period of the state 2, for example, of the state 2? Look, you can return in the state 2 in 4 steps, right? 1, 2, 3, 4. But you can also return in 1, 2, 3, 4, 5, 6. You can return in 6 steps, and then it's clear. Then you can add 2 steps by making loops here. So in 8 steps, in 10 steps, etc. Right? That's why the period equals to 2. Similarly, for all other states, this is the same story. So you see, for the moment, in all the examples, we observe that the period of the state does not depend on the state. And indeed, this is true in general. It's theorem 25. The period is the same for all states. For all states. And this period is then called the period of the chain.
Sorry, do we assume that the chain is irreducible in the theorem?
Yes, we assume that the chain is irreducible because the period is just defined only for irreducible chains. We have defined in this section, we all the time assume that the chain is irreducible, because the definition of the period holds only for irreducible Markov chains, because otherwise, I mean, if the chain is not irreducible, then the period doesn't make sense, because for this chain, what is the period of the state 1? No period, right? Because you never return to the state 1, starting from the state 1. So this definition holds for irreducible Markov chains only. Irreducible. So let me prove this theorem. This is fast and conclude for today. So proof of the theorem. But this is just simple exercise. Let us consider two states, I and J, and let us prove that they have the same period. Since my chain is irreducible, it has the unique communicating class, right? That's why there is a passage from in a number of steps, which starts in I and finishes in J, in some number k of steps, right? And also there is a passage which starts in J and finishes in I, right? Let us assume that the period. So we have periods d of I and period d of J. Look, this loop. Let me call it. Its length L1 of all this loop, right? This L1 is divisible by d of I, right? Okay. Then let us just a second. Whoa. Okay. Let us assume that the periods are different. Well, that the periods are different. If the periods are different, it means that there are different passages from I to J. Right? Because if all the passages go by the same loop, then the period will be the same. So let us assume that the periods are different. Then there is another passage from J to J, and let us assume that its length equals to L2. Then L2, it is divisible by d of J, right? Divisible by d of J. But look, the passage like this, this is also a passage from I to I. It means that L1 plus L2, this is also divisible by d of I, Since L1 is divisible by d of I, it means that L2 is divisible as well by d of I, right? But since d of J was the smallest, was the greatest common divisor for all trajectories, right? for all loops, and this holds. So I can repeat this argument for any loop which starts in J and finishes in J. It means that d of I, it means that d of I should be larger than d of J, at least not smaller than d of J. But no, d of J is larger. Sorry, d of J is larger. D of J is larger because d of J is the greatest common divisor. D of J is larger than d of I. But this argument is symmetric. And similarly, we conclude that d of j is smaller than or equal to d of I. It means that they should be equal. Okay, is it clear or not? Because I think that I explained not very properly. Is it clear or there are questions?
So the inequality of the periods tells us that there is another loop L2.
Yes, because
Which is-
if there is a unique loop like that, it means that clearly the period should be the same, right? Because the length of this loop does not depend on where do you start, right?
Yes, okay.
Then the periods will be the same. But if they are different, then you should have another loop. And then it turns out that you find this relation, but the argument is symmetric. If you make the same argument starting from J, not from I, then you obtain the inequality to the other direction. Okay? No more questions?
So the loop, the new loop is different, not only, but not this length, right? The length of a loop can be the same as L1.
The same, yes, the length can be the same. The length can be the same.
Okay.
No, Camille. It wait. If the periods are different, then it is not the same, because otherwise the greater common divisor would be the same, right?
Right. Yes. Okay.
Yeah. So L2 is different from L1. Why?
There was a question in chat.
Yeah, I'm looking at this. Why was L1 plus L2 divisible by Li? Because look, because L1 plus L2, because you can also consider the loop which consists of the two loops together. You go like this, then you go like this, then you go like this. This is also a way how you can go from the state I to itself. Then, by the definition of the period, the length of this long loop should be divisible by the period of the state I. So it should be divisible by d of I. Okay, so no more questions. Questions 1, questions 2, questions 3. Okay, no more questions. So let us finish for today. I will conclude this story the next time, and also the next time we will have the control work. I think that the control work, it will be like, it will take like about an hour, maybe 50 minutes, and the lecture will take another 30 minutes. Okay, see you.
До свидания.
Счастливо.